பிரபா மேடம் கொஞ்சம் சார் ஜாயின் பண்ணிட்டாங்களான்னு செக் பண்ணுங்களேன்.
Ma'am, HOD ma'am, start பண்ணலாம் ma'am. சார் வந்தாரு.
சார் வந்துட்டாங்க இப்போ. சார் வந்துட்டாங்க. Good morning sir. Dr. Somnath Ghosh.
Sir, your audio is in mute, sir. Good morning, sir, and welcome. And Dr. Lavanya, Head of Department, Civil Engineering, sir. Your audio is in mute, sir. Dr. Somnath Ghosh.
Hello, sir. Dr. Somnath Ghosh, sir. Good morning.
Is it okay now?
Yeah,
yes, sir. Yes, sir. Good morning.
Good morning.
We will start the program, sir. Shortly, within a minute now. We will start now.
Okay.
Madam, start பண்ணிடலாமா madam? HOD madam?
Yes, sir. And
whether we can start the program?
Welcome for slide 40.
Sir, Gopal Krishnan, sir?
Yes.
No, sir.
சொல்லுங்க மேடம்.
Sir, account.
மேடம் ஸ்டார்ட் பண்ணிடலாமா மேடம்? Whether we can start the program, Prabha madam?
Yes, sir, we can start.
Okay.
Sir,
Stella available now?
Sir, Gopal sir, let HOD ma'am start, sir. Ma'am is going to talk.
Sir, Stella will be coordinating, no? Otherwise, I will coordinate,
sir.
no problem.
No, sir, let HOD ma'am start.
அதான் மேடம் அவங்கள இது பண்றதுக்கு இன்வைட் பண்ணி சொல்ற மாதிரி சொல்றேன்.
Sir, let us start, sir. The time is up.
Yes, madam.
You have started recording, it seems, so let it be completed. And I want the welcome
Yes,
slide to be available
yes.
on the when there is no presentation.
Good morning to all. On behalf of the Department of Civil Engineering, I welcome you all for this international webinar series. Now I request our head of the department, Dr. Lavanya Madam, to give the welcome address.
Thank you, Gopalakrishnan sir. On behalf of Civil Engineering Department of SRM EASWARI Engineering College, I welcome all the participants for this second international webinar series for this season, that is starting from the March 21. First one was in inner engineering. Now we are going to the core engineering side. And to brief about the department and college, the college is around 25 years old. We are celebrating the silver jubilee of our college. And as a civil engineering department, it enjoys its 10th year. We have completed 10 years of our existence, and most of our alumni students are working in various countries. And I am happy to share that some of the resource persons for this international webinar are our own alumni students who are working abroad. And I thank, at the same time, I thank our students for participating and showing interest in participating in such seminars. And I welcome all the participants from various sectors who have enthusiastically joined here. Surely, the purpose of your joining this webinar will help you to enrich your knowledge in this pandemic period. And I welcome Dr. SOMNATH Ghosh, Professor from Jadavpur University. Sir, thank you for accepting our invitation in spite of your busy schedule and in this pandemic period. Welcome, and we are eager to hear the speech, sir. Thank you very much for accepting our invitation. Gopalakrishnan, sir.
Yes, madam.
You can start, sir.
Yes, madam. Next, our department video will be shared to the participant for initially for this program today. Since we are the first starting, today is the first day for this international webinar series. Just we want to highlight our department to all the participants. Now in the department video.
Stella?
Stella, you are available?
Yes, sir. Stella, carry on.
Introduction about the chief guest, madam.
She is doing,
Okay,
sir.
sir.
She will do.
Delighted welcome to all. We are truly delighted to welcome you in this international web series. I am profusely overjoyed to take the opportunity to introduce our chief guest. Dr. Somnath Ghosh is serving as a professor in the Department of Civil Engineering at Jadavpur University. He was Dean of Engineering Faculty and Head of the Civil Engineering Department at Jadavpur University. Dr. Ghosh obtained his BE Civil Engineering from Jadavpur University and his M.Tech and PhD from Indian Institute of Technology, Kharagpur, India. He is a member and chartered engineering of the Institute of Structural Engineering in the United Kingdom. He has carried out research in United States and Australia and delivered invited lectures in the United Kingdom, Australia, Singapore, Malaysia, Thailand, and the United States. He also delivered a huge number of lectures as resource person in different Indian Institute of Technology, National Institute of Technology, and universities. He has served as an expert member on several occasions for many institutions and universities. He has served a member of several high-powered committees in All India Council of Technical Education, the University Grant Commission, the Council of Scientific and Industrial Research, the Union Public Service Commission, etc. He has contributed significantly in the area of structural engineering and materials. His major contributions are in the area of high-performance concrete, alkyl activated composite, FEM analysis of reinforced concrete structure, wind and earthquake resistant structure, repair and retrofitting of structure, etc. He has also been structural consultant to a number of key projects at the national level. Based on his research work, Dr. Ghosh has published a number of papers in peer-reviewed national and international journals and also published 6 monographs in international level. His new book on Design of Wind and Earthquake Resistant Reinforced Concrete Building will be released worldwide this month by CRC Press, Taylor and Francis Group, USA. Apart from his research activities, Dr. Ghosh has demonstrated his technical skill by providing advice on industrial projects, and these have been implemented successfully. The repair and restoration techniques adopted from the earthquake damaged structure of Kandla Special Economic Zone through his expertise deserves special mention. His other Northway contribution in the restoration of earthquake damaged assembly building in Sikkim. In addition, his skill in computer-aided structure analysis has been demonstrated through designing 52-meter tall Buddha statue at the top of the hill, Rabangar, Namchi, Sikkim, and Cricket Stadium as Guwahati, Assam. His selection as country head for the division of multinational company in Nigeria speaks volume about his administrative abilities as well as his academic skill and expertise. He is a well-known personality in our country. I request Sir Dr. Somnath Ghosh to enlighten the participant with his precious word as we begin with the event.
Thank you very much for introducing me. Let me now present and then I'll discuss.
Thank you, Stella. Now I request Dr. Somnath Ghosh to deliver his speech. Yeah,
Just a
you can
moment.
start, sir. Thank you, sir. You can start now.
Yes. I have to first share. Can you hear me?
Yes, sir. It is visible, sir. Yes, sir. It is visible. You can put the F by, sir. That is the slideshow mode.
I'll do it.
You can put the slideshow mode, sir.
I'll do it.
Yes, sir. It is now visible correctly. Thank you, sir. You can proceed, sir, please.
Thank you very much. Thank you to SRM University, because basically this college is under SRM University. When Professor Bova requested me to deliver a lecture, I accepted it because I know that the SRM is a good group and they are doing good job. And let me participate in an event with them. Now today, basically I tell you, I'll discuss on high performance concrete. And frankly speaking, that my focus will be towards 21st century. Now, you see, when we are talking about high performance concrete, we really consider these parameters. There are many parameters, but out of all the parameters, these are the most important parameters: strength, ductility, workability, and durability. These are the four parameters you all know. But in many times, we don't consider durability or ductility. We only concentrate in strength and workability, even in research. Now, when we are discussing about high performance concrete, then the durability and permeability I have taken together, then pumpability, because in most of the high-rise buildings, now the concrete is pumped to a particular height. Maybe it's a 20-story building, the concrete is pumped from the ground level. And the challenge is that the concrete which you are getting from RMC plants, the quality of concrete, the same quality of concrete you have to pump it at that level. Quality can't be compromised. So this there are various parameters which controls this pumpability. Naturally, nowadays, this is the scenario everywhere. Naturally, you can't say that I'll not do that. You have to make arrangement for pumping the concrete to a particular level. Shrinkage, you all know, very important. Heat of hydration is also important. Now, when we talk about new generation concrete, at the present moment, then we normally say self-compacting concrete and alkali activated concrete. There are other types of concrete also, new generation concrete. But today, I'll just discuss on these two areas. Now, first, your self-compacting concrete. So many of you heard about it, that what is self-compacting concrete. You all know that where the reinforcement is extremely congested, and it is very difficult to, compact the concrete, even if using high pressure. So in that case, if you can place some quality of concrete which can easily go through the gaps between the reinforcements, even if it is less, because in many situations you will find that at the column beam junction, the stirrup spacing is maintained 75 millimeters for your to make it become earthquake resistant. But if the concrete is not going inside the joint, then whatever you do for the remaining part of the structure, your purpose will not be served. So definitely you have to pour the concrete in such a way it should go to the inside portion of the beam column joints and other portions also. And you don't need to really vibrate separately with vibrator, middle vibrator, or some other kind of vibrator. You don't need that. The concrete will be compacted due to its self-weight only. Now this is a concept. It is not very new. People are practicing now also. In the ready-mix plant, people are using it. But only thing is that, the requirement of the client is changing. So depending on that, you have to make a proper mix design of self-compacting concrete. It is not really exactly same as the other type of conventional concrete. So you have to be very careful. So I have focused those important aspects in this lecture. Now, you see why I'm saying for 21st century, because we want durable concrete, constructible, pump concrete, obviously I have described, more predictable. Means whatever strength and workability you are expecting from concrete, that you must be able to predict it before you go for it. Then it should be greener, because the process should be such so that that the carbon dioxide emission and other things can be avoided, and most cost competitive. Because whenever we are going for this kind of concrete, it is in everybody's mind that the cost will be more. So that is the challenge. That is the challenge you have to accept, and you have to make the concrete, cost competitive. Now you see if the durability is enhanced, obviously it is welcome. And if you pump the concrete and take it at a particular height, like you are supplying water, and you can just place the concrete, no vibration is required. So it shortens the construction time. Now, obviously, I told you that in confined zones, in restricted areas, reinforcement condition, this kind of concrete is very good. And as there is no vibration is required, so there is no noise problem. And at the end of the casting, everything, you can finish it properly. Surface finish will be excellent. So the economic consequences, constructability is important, predictability is important, then controllability and increased service life. You see, constructability is obviously, when I gave you the example of high-rise buildings, there, you have to do it. So you have to make the concrete in such a way so that you can pump it to that level, the highest level. This kind of concrete is very complex. Even if the water cement ratio is slightly, different, what you recommended, in that case, you won't get that. So, before you use it, before you produce it, you must be able to predict its, the workability, strength, and other engineering properties properly. So predictability is important. Not just, trial and you are doing something. No. Controllability, obviously, and if you can go for a very, highly compacted concrete, then obviously the aggressive agents in the environment will not be able to penetrate through concrete, and the service life of concrete will be more. Now the question is that this kind of concrete, whether we will be able to appreciate it, whether it is self-compacted concrete or not. You have to understand rheology properly. You normally don't use the term viscosity in case of normal concrete. You just go for slump. But here, viscosity is very important because concrete is, four-phase materials, stone chips, sand, cement, water, and other kinds of additives, admixtures, and the entire concrete is flowing together. When it is flowing together, suppose it's a pump concrete. If the cohesiveness, the quality of concrete at the phase state in the ground level, if you pump it and if you get something different at the end, that means suppose only stone chip is coming out, slurry is not coming out. All the slurry is coming out, stone chip is not coming out. That means you can't use that concrete because what you have prepared at the ground level is similar kind of thing. You should be able to get it at the highest level in the building. Now the question comes that this kind of thing, this different particle size, density, going together is a multi-phase flow. Naturally, you have to be very sure. So the viscosity is very important. Obviously, the viscosity, when you are talking about viscosity, then obviously there is a term yield stress will come, which is these two things. Normally we discuss when we discuss rheology. Then, to understand this, there are several methods. Several methods are very modern type methods, but at least in the laboratory or in the field, some methods must be followed. That is to understand its filling ability, its passing ability, its flowability, resistance to segregation, volume filling ability, and thixotropy. You see, the thixotropy, sometimes, you discuss, but you don't go into the matter because many people are not doing research in thixotropy, or in the code also they have not specified something specifically for thixotropy. Suppose when a concrete is flowing, fresh concrete, at the same time setting is also taking place. So as the time goes, the workability of concrete is also reducing. But at which rate? How can I define that? How can I define that? Whether the workability is, reducing very fast or low. So, this kind of thing you can express in thixotropic terms. I'll discuss this. Now you see this composition of self-compacting concrete. The mineral admixtures like fly ash or silica fumes, those things are added. Then your water must be there. Chemical admixtures that you all know, many different types of chemical admixtures are used, high reduce, then water reducing admixtures, superpositizers, and the most important is viscosity modifying admixtures. Fine aggregates, obviously, coarse aggregates. So, these are the things, are the basic ingredients in self-compacting concrete. But don't think that whatever you are seeing in the slide, it is restricted to that only. There are many things, but that is not really possible to discuss everything within 1 hour. But my ambition or my objective is to give you an idea, overall idea, so that you can think about it. You can go into the detail of it. And then slowly, you will be master in this particular subject. And then you can work, with many people and develop many things. Now you see the composition, I told you that powder, the fine aggregate below 90 micron, if you go for very big particles, then it is not always give you this, you can say, self-compacting concrete. Now even micro mortars, we are going for self-compacting also. Particles like below 125 micron. And other things, water admixtures are there. Now you see, just try to understand the fundamental approach towards achieving self-compacting rheology. Just you see, you are limiting the post-aggregate content. So it is related to segregation resistance. Superprocessor you are using, it is giving you fluidity. Again, it has got relation with segregation and relation to fluidity. If the material is segregated, you can't use it. Then if you go for very high water cement ratio, then you can't really produce cohesive concrete. It will be segregated. Naturally, if you take all these things together, they are interacting with each other, then only you can achieve self-compatibility. Otherwise, just you can't. Because here, it is just like a fluid. Concrete is just like a fluid. The slump, etc. is, you can't compare it conventional concrete. Even if you can't measure slump, it is just like, fluid. But you will be able to achieve it at a very, very low water cement ratio. And obviously superprocessors, viscosity modifying admixtures, these things have a very important role. So you have to procure these things and you have to cook it properly. Then only you will be able to achieve, self-compatibility. Now the aggregate, the size, quantity, shape, spacing, interparticle separation, combined aggregate packing. So all these things are very, very important because you try to understand that normally the particle size of coarse aggregate is bigger than fine aggregates, and the particle size of fine aggregate is bigger than cement. And again, the particle size of the mineral admixtures like silica fumes is much less than cement. So what is happening? That interparticle gap between the coarse aggregates is taken up by sand. Then interparticle gap between sand will be taken up by cement. Interparticle gap between your cement will be taken by these mineral admixtures like silica fumes. And in this way, you will be able to achieve a very dense concrete. So that is what I am saying, packing, and which you can express in terms of density. So these are the very, very important aspects. Normally, we are not really discussing or understanding or using these things properly. Now, these are the things, very important aspects. Superprocessor, obviously, high range water reducing superprocessor, viscosity modifier, microfine particles like silica fumes, fly ash, etc. Low water cement ratio, low. If you go for high water cement ratio, you will not be able to achieve self-compacting concrete. It's a tailor-made concrete. Why tailor-made? Because your client may ask for a particular strength, particular workability, particular durability, and many other aspects, pumpability, and you have to develop accordingly. So, and obviously, hand mixing is not at all possible. If you try to do it by hand mixing, you will not be able to achieve self-compact concrete. So, use of mixer machine. Use of mixer machine is very important. So, you see, when people are coming to a particular person for mix design in the profession, then one can provide a mix design at a very low consultancy fee. But when his requirement is different, like self-compact concrete with pumpability and other things, obviously that person should be a real expert. And maybe your consultancy will be more. But the advantage is that with little bit of more expense on consultant, you will be able to achieve a much better concrete, and which ultimately you will be benefited. Now you see this rheology, when you are saying, then you try to understand that stability. It controls by segregation and bleeding. You understand the difference between segregation and bleeding, so that gives you stability. Then relative density is compactability. Then obviously your mobility, flow, viscosity, cohesion, internal friction. These are the three important things. Now naturally stability, compactability and mobility altogether is your rheology of threshold. And this is you want to achieve. You have to be very sure about these aspects. Now you see, if you try to understand the mixed constituent, then in terms of, you can say kg per meter cube, you can express cement, and then this, then many other things. These quantities you can mix together and you can get it. Okay. Now question is that when we go for normal concrete, then the minimum cement content, something is specified in the code. But when you are going for this kind of high performance concrete or self-compacting concrete, then you are adding fly ash also. You are adding many other things. And fly ash indirectly is also kind of binder, contributing as binder. So that you all know. So this is just an example, Now you see, you have to measure the rheology in the field and also in the laboratory. Then the slam flow or T50 flow, refunnel, or this is T5 minutes, chairing, U-box. There are 10 such methods which are normally used in the research, in the laboratory, not 10 if you consider the rheological aspect in detail, then it may be much more than that. But at least in the laboratory or in the field, you have to use these 4 methods. Now, this method gives you filling ability. This particular slam flow method is also filling ability, chairing, passing ability, refunnel, like that. So these are the tests, different tests, and they are giving you these properties, which are very important. Now you see, this is a typical slam flow test, right? So if you just go to any code where they have specified exactly what should be done, but this is actually gives you some idea about the flow. This is V funnel. You see, just they fill up the cone, right, with concrete, and it is closed initially, and then it is removed. The shutting is removed, and they calculate the time. How much time is required just to make this cone empty? That time is important. Okay, and you see, this is a kind of test, jading test. It is very similar, this kind of vertical rods they are provided as if the concrete is passing through the reinforcements. So this is the cone, you are filling the concrete here, and then when you are just lifting it like this, then concrete is flowing, like this, that is passing through this, vertical bars, like reinforcements. And what will be the ultimately, what is the flow that we are measuring? What is the diameter of the flow that we are measuring? Now you see, this is another kind of test. This is a YouTube test. So if you have a, just if you block it here and fill with the concrete, and then you remove the shutter, then what will happen? It will come this way. But if it is water, then both the levels are same. But in concrete, it is not like water, so there will be some difference. But if the difference is less, and if the concrete is cohesive, means it will give you the self-compacting property. So this is another kind of test. Now you see, there are different criteria are there for this kind of test. So the maximum value is this, minimum is this. This time. So all these values are given. So if you do this test, and ultimately if you find that this is coming within this range, that means your concrete will ultimately be, it will be a self-compacting concrete, no doubt about it. Now you see, we have given, we have tested several mixes in the laboratory for so many years, because I am in this profession for 40 years, and our particular concrete technology group is very strong in the country. So these are the tests we conducted long back in 90s. That time we achieved all these things. Now it is even better. So you see, this is the coarse aggregate, fine aggregate, then the GGBS slag, then silica fumes, metakaolin, like that. I have given you the quantity per meter cube. And the superpasteurizers, viscosity modifying admixtures, how much. So like that, there are different types of mix, CO, then FL2, like that, FL1, right? So if you go through this slide, then you will understand that I have changed these quantities. In many places I have not used it, right? And ultimately, this particular test I have done it in Series A. And again, with the knowledge, we went for Series B, right? S1, S2, S3, different kinds of mix, Series B. And all these things are varying, right? You can just play with it. Now, ultimately, if you do it, ultimately, at that time, we could produce up to M60. Now, we can produce even, higher strength of concrete. I'll tell you, if the strength is, if you're expecting very high strength, then there are other problems also coming. You have to take care of those things. Now, when we are doing all these things, trying to achieve self-compacting concrete, then you have to understand the compatibility of the ingredients, cement, sand, stone chip, admixture, all these things are ingredients, and whether they are compatible or not. You see, if every member of a group, if they are very compatible with each other, then that group becomes very strong. Same thing. So that is why the compatibility between the ingredients are important. We are not checking it. We are using a particular, superpasteurizer or viscosity modifying admixture with a particular type of cement. No, it is not compatible. So a particular type of cement is compatible with a particular type of viscosity modifying admixture or a superpasteurizer. So you have to first understand that, whether the ingredients are compatible or not. And then you have to select that ingredient accordingly, a particular cement with a particular viscosity modifying admixture or superpasteurizer. Then all the ingredients are compatible, and ultimately it will give you a very good self-compacting concrete. Like, I told you that if all the members are compatible with each other, then the group becomes very strong. Similarly, the performance of self-compacting concrete will be extremely good. Now you see, the strategies to limit negative occurrence, that you have to also keep in your mind, because durability is also important. So I'm just focusing you a few points, but those who are really interested to do some kind of just a moment. Hello. So you see, you have to limit total alkalis in the mix, sodium, potassium, etc. Especially, you have the contributions coming from cement. Then testing of aggregate, because all the aggregates are not, recommendable if they are reactive. Because when you are adding water, then what is happening? In any cement, calcium hydroxide is liberated, whatever we are using normally. Now, if that calcium hydroxide reacts with that particular aggregate, then there is another problem. So you have to be very careful. So testing of aggregate for reactivity. Provide additional reactive silica, form of fly ash, all these things you can do it, right? And now also better techniques are also used. Why? Because these are all reactive silica or fly ash, silica fumes, all are, pozzolanic materials. So you know that if there is pozzolanic material present in the mix, then whatever the calcium hydroxide initially liberates, that reacts with those pozzolanic materials and ultimately gives you more gel and it makes the concrete alkali free, which is definitely good, because if the calcium hydroxide exists or remains in the concrete, that is not good for the concrete, good for the health of concrete. Now you see that few other problems: inadequate compaction resulting segregation. You all know. Micro cracks resulting from shrinkage thermal. So you have to be very careful of shrinkage, thermal-stresses. If you don't take care of those things, then there will be huge shrinkage crack initially. Then bleeding is another problem. If you keep the concrete in a particular place, you will slowly find that even if you do nothing, the water is coming out from the concrete. So concrete should be able to hold the water, whatever you have given. If it is coming out, it will become harsh. Then volume of pores and capillaries, that is to be controlled. Then distribution of pore and the discontinuity. If there are pores and the pores are not interconnected, that is bad. Because it happened to the Eurotunnel that the concrete was very, very good, high performance concrete, but the interconnection between pores were not there. As a result, what happened at a particular temperature, when the temperature rises to a great extent due to a fire, what happened that the water entrapped within the concrete, that produces vapor, and that vapor produces huge pressure inside the concrete, and ultimately that concrete bursts. That happened to the Eurotunnel long time back. But now people are careful that yes, pores should be reduced, but that doesn't mean that there will be isolated pores. Pores should be interconnected. Then what will happen if the pressure in a particular pore increases? Then it can, just release to the other pores. So the pressure will not be very high. So these are the things, you have to understand. Now, when I am talking about all these things, unless you really go for microstructural study, then you will never be able to understand that what exactly happened there. It is just like a story now to you. But if you study the microstructure, then you will be able to really appreciate, right? Now you see the reduction of permeability. If you can reduce the permeability, that means the durability will be more. Suppose the concrete is in a saline environment, or in acid or alkali environment. Now, if those things, try to percolate through the concrete, and if it percolates, then what will happen? the bond between the aggregates will be disturbed. The interfacial zone will be disturbed. And that interfacial zone, if it is disturbed, everything is disturbed. So the property of the interfacial zone actually contributes to the property of concrete. If a concrete is ductile, means the interfacial zone is ductile. If the concrete is of very high strength, then with the interfacial zone is of very high strength. Right? And all you know that the interfacial zone, that really, the particle size is very, very, very small at the nano level. So you have to understand the interface. So now people done research on concrete, mortar. Now people are doing research on the interface. Not now, long time back, those who are researchers, because they know that if they can improve the interface between the particles, that means they are actually improving the concrete properties. Now you have to avoid bleeding, blocking the capillary channels, proper curing, very, very important. Controlling the water-cement ratio, very, very important. If you have water with cement ratio, just, don't control it. It will be a porous concrete. No use of it. Additional hydrophobic materials that you can, provide just to reduce the permeability, right? Now, pumpability. To some extent, pumpability can be equated to resistance to bleeding. If you can stop bleeding, then the pumpability is better. Blockage, pumping failure occurs when the mix segregation under pressure. That means the pressure you have to control. If the pressure is not controlled, then it may happen. Bleeding of, this water, segregation of water, all these things due to gap created aggregate, that's to be avoided. Now you see that you will be able to produce a very good pumpable concrete if all the sizes of aggregates are present in the concrete more or less in equal quantity. I'm not saying exactly equal quantity, more or less. That will give you packing, and you will be able to achieve cohesiveness through use of viscosity and modifier admixtures. You can reduce the water cement ratio by using your high range water superpressurizers. So all these things you can do it. So keep this thing in your mind. Shrinkage also, drying shrinkage and also carbonate shrinkage, that is, you don't want it. Then you have to, you have to take care of the aggregates and also the paste. That's very important. You cannot allow loss of water because that will lead to high shrinkage, right? Shrinkage is largely dependent on total quantity of water in the mix. If it is less, then shrinkage will be less. Nesting modulus of coarse aggregate, proportion of aggregates. Now gypsum content of concrete influences shrinkage, obviously. So in one way gypsum is helping, but in the other way, the concrete property is also always the presence of gypsum is not good. So there should be a limiting quantity of gypsum. Okay, if I someday discuss with you only about cement, only about the basic, aspects of cement with your reaction mechanism and all, then you will be able to understand better. Now let us try to discuss another thing, which I told you initially, which will be extremely popular in 21st century. It is already become very popular in most of the country, in Australia, USA, Britain, Ireland, everybody is using it. In our country also, people started using it. They're manufacturing many things. But still, I must say that we have to take it forward in our country. I know many persons are working on alkali activated composites. in your university also. Now you see that you have to understand sustainability. And then you will be able to understand that why this change is required. Why normal Portland cement could be replaced by something, right, in order to achieve sustainability. Now you see that the limestone and all these processes did some things. Ultimately, what happens? It liberates your carbon dioxide. There is some figure given. Okay. In energy terms, some figure given. Right. But ultimately, carbon dioxide liberates, which you don't expect, which you don't want. Because global warming is because of the liberation of carbon dioxide. We have to limit it. Now you see, after this hydration product, you adding this water, then hydration products are developed. Again, carbon dioxide is developed. During hydration process, again the carbon dioxide liberates. So during manufacturing, during producing concrete, carbon dioxide is liberated. Now this is not expected. We don't want this. That means we have to come out with a solution where the carbon dioxide emission is reduced. We want carbon-free environment. We cannot make it zero, but near to that. And you see, if you can, produce something which is greener. Greener means, produces less carbon dioxide during manufacturing or other situation. You see, now worldwide there is something new protocol, is carbon credit. Carbon credit means that if you are using some material where the carbon dioxide emission is less than the conventional material people are using, then your company will get some tax benefit. And some company are dealing with it in our country, in different parts of the country, maybe in Chennai also. If you can save your tax because of your carbon-free, carbon dioxide-free material production, then obviously your profit will be more. So in one way you are making more profit, in other way you are making the environment carbon dioxide-free. So global warming will be reduced. So that is why some alternate material is definitely required, right, to replace Portland cement or Portland Portland cement, conventional cement. How can you do it? That is the big challenge. How can you do it? Right? Now, you see, the alkali activated composite, what it is, I'll tell you. Initially, this is proposed by a very renowned professor, Professor Davidovitz. But initially, he worked in different areas of material, not exactly in cementitious material. He started with something with other kinds of material, but not, cement-based materials or cementitious material like we are using, civil engineers are using. Later on, he has contributed in those areas also. And if you go to Google, you will find another name, Provis. He is a professor in Sheffield University, UK, and he has also contributed a lot, right? I'll discuss you about these persons because this is the kind of thing. Even throughout the world, very few persons they have, real contribution towards this particular subject. Even, very good books are not available always, right? So still, I'm telling you that, you can contribute a lot in this subject. Now you see the alkali activate binders are synthesized by thermal activation of solid aluminum silicate source material. That means the source material which contains aluminum silicate, such as fly ash, metacholine, ground granulated dust furnace slag, ice husk, etc. It contains aluminum silicate with alkali metal hydroxide, sodium hydroxide, potassium hydroxide, or sodium silicate, potassium silicate, some silicate solution. So there is no such, no conventional cement. Just fly ash and all these things, hydroxide, some silicate, mix together, you will be able to produce the gel. And those gel will be able to bind the aggregates, and you will get a concrete. So you are using this fly ash or GGBS, ice husk, which are normally considered as waste. But when the moment you are adding this metal hydroxide and silicate solutions, many other things are there. I'm just telling you in general. Then you are producing a very good binder. So just from waste material, you are making gold. Very good. Gold means, I am saying, very useful material. Now you see, you have to understand the scenario in India about fly ash, because the fly ash is the very popular source material which is used in alkali activate composites. So you see, these are the figures. I don't want to, but these are very 230 to 50 million every year. And then high ash content. So just go to the figures. So just imagine, this is a figure 170 million by 2000, now it is much more than that, 250, cost 250. So all these things are, a problem. It's a real problem. But fly ash is rich in silica and alumina and has full potential to use as one of the source materials for geopolymeric binding. So it contains this. Right? This contains this means that fly ash is used in these areas, in cement manufacturing, land development. But still I tell you that fly ash is not properly utilized to produce binders, right? You alternate to conventional cement, which we call as alkali activated cement, or you can say that alkali activated composite. Now, by this time, I think you have understood that when I am talking about alkali activated composite, there is no question of using conventional cement. It is just fly ash or blast furnace slag or metacholine. These are the prozolering material together with your some metal hydroxide, some silicate, metal silicate, or many other material. So why I am preferring this simple production technology? You can develop all this higher mechanical strength, very high composite strength you can achieve within lots of time. Curing, fast curing can be done. Shrinkage and creep can be avoided to a great extent. Extremely good resistance to sulfate, chloride and alkalis. Excellent resistance to fire. At least up to 1200 degrees I have personally worked on it, and very good. Freeze thaw we have tested, very good. And you will slowly understand that this there is no question of alkali within the composite. Because alkali, when the reaction takes place, then the alkali is consumed. So there is no excess alkali which will be present in, and that is your no alkali aggregate reaction, highly durable, right? So anybody is asking any question?
Yes, sir. They will be putting in their chat box. Then we can. I will give the feedback to you. Participants.
Somebody just now I heard somebody is shouting. Why he is shouting in between the lecture?
No. Yeah. One person now. Yeah,
No,
muted,
why
sir.
are you doing this?
No.
I can't
No,
understand.
sir. Unfortunately, no, unfortunately, he
You are
unmuted. Now again he muted, sir. You can continue, sir. You can continue.
organized properly. Now you see, the alkali activate composite, is a chain of network. Don't think that only fly ash. Don't think that silica alumina. Don't think this way. You can develop alkali activate composite just bypassing your conventional cement, and you will get the binder, which is very useful in different way. So these are the different ways one can develop. I have not really worked in these areas, in this phosphate and all these things. These areas I have not worked, but I have worked to great extent in these areas, right? So those who are very young, professors, students, PhD scholars, and all these people, and that is my objective, just to give you the insight of the subject, so that in future one can develop something and which will be useful to the industry. Otherwise, I can't understand why we are learning so much, why we are doing research, unless our next generation comes forward and do it. And I'm sure that the next generation will come and do it. Most of my research scholars are very young and contribute to a great extent. They wrote books also. Now you see, this is the kind of thing happening. When you are rather the source material like fly ash, when it is coming in contact with alkali, because you are adding alkali, then dissolution of solid alumina silicate source, that means the fly ash, it dissolves. Silicate species is inactivating solution. The sodium silicate obviously is there. So when these two are happening, then rearrangement and exchange between dissolved units is happening. Then gelation, gel forms. Then solidification and hardening. And then your ongoing gel alignment and crystallization. So this entire process takes place. It's very easy to understand. Those who are interested to do work in materials, in concrete, I think they can do many things. They can just play with it, right? So this is the process involved in alkali activation, right? Now, if you just compare with your ordinary Portland cement with your this geopolymer, right? Then the percentage of calcium, this part is very high, and if it is very high, obviously it's not good. Why? You understand. Silica part, yeah, it is very high. It's good. That's why it's good, right? So you will slowly understand that why we are getting better product. Now, why I'm saying geopolymer? Because here I'm discussing about fly ash plus, alkali and silicate. It will give you a binder which is polymeric in nature. And fly ash means it is from coal, means geo means mitti. And That's why, we call as geopolymer. But nowadays, people are not really calling as geopolymer. Rather, they are using alkali activated composite, that particular term, because it's a general term. If you use slag, then the polymeric reaction is not taking place. I'll come to that. Of course, today it is not possible because we don't have time. Let me ask you a question to the organizers that shall I continue or your time is over?
Yes, sir, you can continue, sir. No problem.
If you allow me to continue,
Yes, sir, you can continue, sir.
then I'll take another 15-20 minutes. Because this is in the midway. Oh, you see the manufacturing procedure, this is very important. Those who are doing research in this area, they should be extremely careful about it. Sodium hydroxide pellets are dissolved in water and make the solution of required polarity at least 1 day before the casting, not on the same day. You won't get any result, good result, if you do it on the same day. Sodium silicate and sodium hydroxide are mixed together at least 1 day before casting. Then of course, this is we are not doing it now because of different other problems. In the winter it is different, summer it is different. You can do it 3-4 hours before casting. Then fly ash and aggregates are, you have to dry it and mix it together, dry mixing. And then you have to add all these things, slowly you do it. And then finally, you will place in the mold, and after say few hours, or maybe after 1 day, you can take the specimen from the mold, and depending on your requirement, you can put it in the oven at a 60 to 90 degrees centigrade, maybe for 24 hours, maybe for 48 hours. All these things are, you can, I'll tell you in detail. So, this is the manufacturing, very simple, very simple. Then the tests are carried out. Bulk density, workability, initial setting, all the things you know. Softivity, of course, you don't know, probably. UPV, you know, diet composite strength, MIP, not normally used always, but this is required. XRD, XRF, and same, scanning electron microscope. These are the microstructural study which has now become compulsory in research. You have to do it. Otherwise, you can't convince the industry people. They will ask you several questions, you will not be able to answer it. Now, I'll just give you an overview about it. But I have written 3 books on this subject, which are available in the Amazon. And a recent book published by one of our very bright student, a research scholar, Kushal Ghosh, recently with CRC, with your Taylor and Francis group, a recent book. But that is, of course, he has concentrated in fly ash and slag, right? But you have to go through those books if you want to get all these things in detail. Everything is given. Many other things are given, which I will not be discussing here, right? And later on, within a year, you are expecting that I'll be able to give you one more book on blended geopolymer, blended alkali activated composite. Now, this optimity test, it is a kind of, test which indirectly gives you an idea about the absorption of water, right, through capillary action. Because unless you don't know, then if the concrete is exposed to a particular environment, and suppose the reinforcement is there, and if you don't know about its porosity, about its, the transmission of water due to capillary action, then you will not be able to understand that when the saline water or acid, all these things will attack that reinforcement inside. That's another problem. The concrete must be good, cover must be good, so that, it should not be able to attack the reinforcement inside. Anyway, this is a very good subject. I'm not going into detail of it. Only thing I'm just referring this ASTM code, right? And we have developed methodology, and we have several publications in ASTM. Now, you will find that when the water is absorbing and you are calculating how much water is absorbed through that particular test, not any test, then you will find that it is increasing, whatever is increasing. And then after a particular stage, after a particular time, it is becoming flat, right? Then the slope of this particular curve, tan theta of that, is known as primary subtractivity. And the slope of this particular curve, rather it is equivalent to a straight line, that is under secondary subtractivity. Now, if you want to really understand the durability aspect properly, then you have to study on the ratio of primary subtractivity to secondary subtractivity. Right? In my books, everything is given very clearly, and this in ASTM publication also you will find all these things. And if everything goes all right, within a year you will get one more book. And there also, I have related this durability, strength, and all these things with subtlety, absorption of water, all these things. Because these are the things very important. Unless you understand this, you will not be able to assess durability. Even we have developed the model for durability index. Because these are the questions you have to answer, right, to the industry people. Otherwise, they will not accept it. They will not go into the detail of reaction mechanism. But they have got their own way to understand whether you are guiding them in a proper way or telling something rubbish, right? That they have got that level of intelligence. So in Delhi, one company is manufacturing, they are in regular contact with me. Now you see, this is the chemical analysis which will go for EDXRF. And you will get this, oxides, how much mass percentage, you will get it through this instrument. Very sophisticated instrument. You may not have in your civil engineering department. It may be in some other department. It may be for central facility. Doesn't matter. You go there, give you a sample, they will do it for you. This is just a result when I use the fly ash from Kolkata thermal power station in near Kolkata. UPB, you all know that what is this. Now, here I must tell you that when you are getting this velocity is around, say, 4.55, then you are saying it's a good concrete, right? But in case of your alkali activate composite, you won't get that high if you compare with normal concrete. But still we are claiming it's better. It is dense. Its durability is high. Everything we are claiming better. Why? Because due to the polymeric reaction, the material is cannot be compared with normal concrete. So due to this polymeric change, or the presence of polymer, whatever it is, the pulse velocity decreases. Pulse velocity is very high in case of metals like steel, copper. Pulse velocity is very high. But for synthetic material, polymeric material, it is less. But polymeric materials are better. So that's why the kind of ultrasonic pulse velocity test need to be done, and you have to say that yes, even if you don't get 4 or 4.5, even if you get 3, 3.5, it is good because it is polymeric in nature, showing you less result. Less value. X-ray diffractometer, this is very important. You must have a central facility, and from there you will get a curve like this, and different types of material develop from that it will show you towards this maximum in fly ash. Then scanning into microscopy, this is also maybe a central facility, right? You can understand the microstructures depending on the resolution of the scanning electron microscope. Now you see, just see the microstructure of alkali active binder. See, fly ash before reacting with sodium hydroxide, it is like this. The moment it is reacted with sodium hydroxide, it becomes, so dense. After formation of gel and all, it becomes so dense, right? These things, you can only understand through your you can say through this scanning electron microscope. Otherwise, you will not be able to understand the microstructure. Now you see here with different sodium alumina ratio, one is 0.46, 1.60. Right? So it is 0.46, it's 0.60. It's much more dense. So this is, from your result, you will get that it will absorb more water. That means the micropores are there, much more than compared to this. So if this changes, how the microstructure is changing, that one should understand. That is why this kind of test is very important. And I must say that slowly in concrete technology course, the microstructural part, you make it compulsory. Nowadays, if you try to publish any paper in very good journals, without microstructural study, you will the paper will be rejected. You won't be able to publish in most of the journals. Similarly, you see that silica alumina ratio, if you are changing from 3.7 to 4.3C, it is becoming cancer. So these are the things, unless you go for microstructure test, scanning electron microscopy, you can't be able to understand. See, these are the things, right? 4662. And the corresponding, the extra results are there. So all the picks will tell you which one is more, which one is less, like that, right? Someday, we can discuss only on microstructure. That will help you. Now, another test we are doing, the marker intrusion pore symmetry is very, very important. Very costly. You may have a central facility, but you will be able to understand. So, MIP is used to investigate total porosity of geopolymer or alkali slag, which measures the total intruded volume of mercury into the specimen. What they do, they try to intrude mercury by putting high pressure. And the mercury is going inside. They are measuring how much mercury is going inside, volume of mercury. And from there, they are trying to predict the pore volume, maximum pore diameter, etc. So, this is the kind of thing. Okay, it might be based on the fact that non-weighted liquid, mercury, one having contact angle greater than 90 degrees, will only intrude capillaries under pressure. And these are the things, relationships are there, to which pressure, contact angle, diameter of the capillary pore, all these things can be related. Right? Very easy. But only thing that you have to be careful. At the end of the test, you will get a graph like this. In the computer, it will come like this, right? So this is cumulative volume of mercury intruded, and this is your pore diameter. So this is very, and this will give you a very good idea about your presence of pores, pore diameter, total quantity of pore in the composite. Everything you will get. Unless you understand it, then how can you say that why that particular material absorbs more water? Because more pores are there. But what is the pore diameter? What is total pore volume? So all these things are very important. Now you see, this is now I'll show you some result. This is a kind of test we did it long back, using fly ash, and that's why I've used the term geopolymer, because fly ash, alkali, silica, metal, sodium silicate and all, ultimately give you some polymeric material. And that's why I could use the term geopolymer. But nowadays, I am not using the term geopolymer for different controversy. I must be sure whether at all geopolymeric reaction is taking place or not. Like, long back, when people used to add alkali and silica, or, the sodium silicate in slag, in blast furnace slag, they used to call us geopolymer. But then, throughout the world, they said, why are you calling geopolymer? Why the polymer term is used? Because no polymeric reaction is taking place. It happened to me while publishing a paper in ASTM. What I did, I went for NMR test, and through NMR test, I found that there is no trace of polymeric reaction when blast furnace slag and alkali and silicate are reacting together. And that's why you must be sure that there is polymeric reaction, and then you should ultimately tell people. So that's why now I'm generally using alkali activate this particular term. Geopolymer, we can always use it for fly ash because it is real geopolymer, polymeric. Now you see, this results are quite encouraging. You see, with fly ash, alkali and silicate at 28 days, just see how much result you're getting. Right? This 48 you can get after 3 days curing also, heat curing. See another set. Another set. Here also you're getting 35, 39, 40. Quite good. Of course, I have varied these things. We don't have time to discuss all these things in detail. Now you see alkali content is basically this ratio. Alkali content is expressed in terms of basically this ratio. 85 degree temperature we found best, 48 hours. Silica content 4%. It means this ratio is 4. Then if you change it, this composite strength is increasing. See there's 7. That means whatever result I have shown you in graphic alpha. It has gone up to 50, very close to 50. This is you see that water geopolymer solid means fly ash. Or if you use fly ash and slag both together, then at a particular water geopolymer solid ratio, source material ratio, water source material ratio, you are getting very good result. But beyond that, it is decreasing. You have to be very careful about water solid ratio. This is, sand and fly ash ratio and composite sand. Right? If it is reduced, then see you are getting the higher strength. You are getting higher strength. Obviously. Then you see this is the curing temperature. From 40 degree to 120 degree. We have varied it. We found that around 85, around that, Beyond that, even if you go for higher curing temperature, it will not really give you a better result. Slightly better. That's why we fixed it to 85 degrees. There are many other aspects also. Hours of curing, 10 hours, 20 hours, 30 hours, 40 hours, like that. Up to 80 hours we did it. And we found that around in this, 50, it is good. Beyond that, we are not getting a lot of advantage because of duration of hours. Because if the duration of hours is more, that means your energy consumption will be more, cost will be more. You see, if you try to understand the alkalinity of the specimen under sulfuric acid, because acid, you know that how it really reacts with your geopolymer. See, here you are seeing pink color. That means if you spray phenolphthalein, it becomes pink. That means there is some alkali there. But slowly you see the alkali is vanished. No alkali. It is consumed by this acid. It's good. So it is good against the acid. Now, this is say after 9 weeks. It is like this, after that, after that. These specimens we have done with different, composition. So these are the tests you should perform. And if you emerge the specimen within 10% sulfuric acid, then how the strength is decreasing, right? With your number of weeks, 3, 6, 9, we did it up to 24. Now people are doing much more. Now this is with, nitric acid. Previous sulfuric acid, it is with nitric acid, right? This is the weight change in case of sulfuric acid. So why I am showing you all these things? Because you have to be very sure about your research program so that you can convince the industry people. Otherwise, you will be just publishing a paper. You may get some credit in your promotion. That's all. But I never worked that way. Whatever I did it in my 40 years of career, I always translated to the industry. Otherwise, just for publishing papers, if you do it, after some time, you will not be happy. You see, just with some observations, I'll close the lecture today. You see, this is a kind of observation we made in case of blast furnace slag. Blast furnace slag paste composite activated by sodium silicate and sodium hydroxide can produce in normal temperatures and water curing. No need of heat curing is required under water curing. Now we have produced this alkali activated composite with slag and fly ash under water curing, because that is the demand of the industry. They don't want to go for heat curing because it consumes cost. Cost is increased. They want water curing. Now you see, the composite strength is increased as the silicate ratio is increased from 0.2 to 0.8. Right? So it is up to this, at 0.8. Pulse velocity, of course, 3.7 is around we have seen, right? It is also, we have seen it is increased with the increase in silicate ratio. So silicate ratio has got an effect on pulse velocity also. Then all these things are relative doses, increasing silicate ratio of 1, reduces porosity in terms of solubility, which I told you. So these are the different, types of, observations which will help you just to read out. You will be able to understand it, right? Is increasing in silica content in this mix decreases this 0.8. Then again, silica ratio, wide microcracks form at the interface of CSH. That also we have seen in the microstructure study, right? It happens. It ratios like this. That is a negative thing. Microstructure inquiry showed that the pores reduced as silicate ratio increases to 0.8%. So all these things, regarding pores, using, Na2O or K2O, how the things are changing. Okay. You can use sodium hydroxide, you can use potassium hydroxide, but you will get different results. If you mix it in a particular proportion, sodium hydroxide, potassium hydroxide, you will get different results. Several things are there, several things. It is not really possible for me to describe anything here, but I'm just giving you glimpses. You'll be interested. Those who are good in research or want to do something new, they'll be very happy. So these things, tensile strength. Then regarding calcium silica ratio, because calcium quantity is very high in such slag. And water curing we have found. Right? So these are the different things. So I'm really looking forward to blended alkali activated high performance composites. We have worked a lot in blended alkali activated high performance composite with 6 different types of source materials and combined together in different proportion and activated in different way, and particle sizes, these, that, differing temperature, many things we have changed, and you produce admixed blended alkali activated high performance composite. And also we have got the prediction model, which I was telling you we have not discussed here, but prediction model that is available in my book also, in my 3 books. And ultimately, we want to get better alkali activated composite, high performance composite, just by blending different materials, not from a single source material, it's just blending. And these are the things: engineering properties, durability, prediction model, reaction mechanism, and the appropriate testing method. The flow table method or whatever method you are using for your flow measurement, or even the rheology and all these things, that is not really, which you are using for concrete and concrete, can be used in this kind of composite. So we have to come out with appropriate testing methods, which we have developed to a great extent. So I hope that within a year, I'll be able to, hand over a book on this thing based on our detailed, analysis and the study, and also the prediction model, different aspects. I hope that I'll be able to deliver it within a year. Now, lastly, I must want to say that one should never be complacent, but should be ever alert for new problems, new solutions, and new opportunities. One should never be complacent. Right? You can do many things. Those who are young, they can do many things. You can make a group and go for different kinds of study. I can only assure you that I don't know how many years I'll be in this world, But if you really want to take my advice or discuss with me about something, I'm always with you. Any moment, any time, just call me, fix up a time and discuss it. Okay? Now, I must say that, that the SRM,
Thank you, sir. Thank you.
enough.
There are some, yeah,
Just a minute.
yes, there are some questions, sir.
Just a minute.
Can
please.
you answer for the question? Some questions are from the participants.
Gopalakrishnan,
I'll
sir.
answer.
Sir, wait.
Yes,
Wait a
madam.
minute, sir. Sir wants to say something. Just a minute, sir. Sir, kindly continue, sir. Somnath, sir, kindly continue, sir.
I think, let me show you this slide. If you have got constant of time, you could have told me earlier. I just want to give with lots of love and affection. Thank you very much. This is the slide I wanted to present. You are not giving me
Thank you,
even
sir.
one.
Thank you.
What is the problem with you? Anyway, and the questions are welcome. Anybody can ask any question. Please ask me question if you have any question.
Sir, I will read the question, sir. I will read the question.
Okay.
Why always sodium-based or potassium-based hydroxide are used for research?
Why? It's alkali. And the alkali is required. Without alkali, how can you dissolve this source material? How can you do it? Are you working on this subject? You personally? Are you working on this subject?
No, sir. There is the questions from the participants. Milan Gupta, Milan Gupta, you are available.
Milan Gupta, let him.
Yes, sir.
Yes.
Hello.
Yes.
Yes, I am Milin Gupta.
Milan, what is your problem?
Sir, in the research, always we are using sodium-based or potassium-based hydroxide, or activators are also based on sodium and potassium-based. So no other alkaline activators are available for the research in geothermal concrete.
Actually, we are trying to develop this kind of compost with phosphate-based also. But I have not yet done it. That's why I have presented it. But whatever I have done it, whatever you say, based on that, but in detail. You can always go for different type of, activities. Next question, please.
Okay, sir.
Next question, please.
What is the optimum water to geopolymer ratio that can be adopted in concrete?
You see, in alkali activate composite, I showed you, it is around 0.3. If water by source material, ratio is 0.3. If it is, your mix is very harsh, in that case, you can go for, plasticizers. Of course, the plasticizers should be compatible with that particular source material. And we have used it successfully. Next.
There is another question. Can we use this cement in green building construction?
This is the kind of thing we have developed that is without conventional cement. This is a particular type of binder. This is actually serving the purpose of cement. Next. Any other question?
Participant, any other questions? You can put it in the chat box.
My dear participants, if you have any question, you can always call me, take the phone number from the organizers and ask me. That is not an issue. And those who are interested, please go through the different things, different literatures, and have a very good base in the subject.
Okay.
Yes.
There is another question. Sir, shall we replace both the fine aggregate and coarse aggregates with some sustainable materials in self-compacting concrete?
No, you can use different types of coarse aggregate and fine aggregate, but only thing is that, it should be cohesive. And the properties of self-compacting concrete is to be established. And the aggregate should not be reactive. So that's why I told you several things. If you think, think it as a whole, then you will get the solution. But if you use some reactive aggregate, then that will be a negative effect. Main thing is, that you are improving the interface. Self-compacting concrete means you are improving the interface. And that is ultimately giving you this. And with your, slight changes in particle size distribution. Particles may be anything. But only thing it should be compatible with the other ingredients. Anything else? Any question?
Any other questions from the participants?
Generally, that after this lecture, they think about it. And later on, they contact with different persons because all the persons are not really active in this kind of research. Those who are interested, they are contacting us. Okay, and you have recorded the lecture, so you can give it to all and send me a copy.
Yes, sir.
Whatever you have recorded,
Yes, sir. Yes, sir. We have recorded, sir. We have recorded.
And download it. After that.
Yes, sir. We can download, sir. We can download.
And you send me the file.
Okay, sir. Okay, sir.
If there is no question,
Prabha, madam.
Conclude.
Yes, sir.
Yes, sir.
On behalf of the Department of Civil Engineering and also the organizing team, EASWARI Engineering College, I thank Dr. Somnath Ghosh spending his valuable time coming over here and presenting a nice presentation on high performance concrete. Sir, you have covered all the areas of self-compacting concrete, then geopolymer concrete, and also the basic durability test, and also the XRD and just so on. Thank you, sir, for your wonderful session. Thank you, and very informative. Thank you.
Thank you very much. I am closing the computer.
Okay, sir. Thank you. Thank you, sir. Thank you.
Thank you, sir. Gopalakrishnan, sir. Gopalakrishnan, sir.
Participant can fill
Sir,
the
kindly
feedback
share,
form.
sir, kindly share the thank you slide, sir, for the YouTube streamers. They avail the feedback link. Kindly share it, sir.
Feedback form. Already feedback form has been shared, madam.
Sir, that is for the Google Meet. For YouTube, we have to share through the slide one.
Okay, slide one. I will share, madam, now.
Yes, sir. Thank you, sir.
Participants, yeah, this is the feedback link for the morning session.